Let me just pull up my slides. Okay. Okay.
Yes.
Okay.
Great.
Thank you for having me. It is a great honor to be in the symposium and present some of the concepts related to resilience of basically energy infrastructure system as a whole. So basically in this talk, I'm going to talk about the energy supply resilience in general, and also we'll look at some of the technologies that facilitates such resilience. And these technologies are basically currently under development. And with these kind of events that we see during this recent years, and it is going to grow probably, then the essence of these technologies would be more evident for the customers and also the society. So let me start with the very first kind of and basically the most important engineering system that was built, the largest one that was built. So Edison started the very first power system in 1882 by building a generator and wiring that all the way to the power outlet and the customers. The system was very primitive. It was a DC system. But then later in 1930s, we saw these isolated power systems, small power systems being developed. And they were combined to basically form a very large, interconnected and sophisticated power system. These electricity systems now are basically the backbone of all kind of technological advancements that are contributing to the well-being of the society and the human. You would see a lot of home appliances, communication devices, computation devices, and they're all using electricity. And the National Academy of Engineering announced that electrification is basically the most important engineering achievements that improve the quality of life in the 20th century. And the one after that was basically automobiles. So this is the current kind of structure of electric power system. We'll see different sections. We'll see generation, which is basically converting other type of energy sources into electricity. And then in order to transmit over long distances, we're basically increase the voltage on the transmission level and transmit the power with very small loss. And that's why that we actually increase the voltage. And then once we are getting close to the customer, then we're reducing the voltage because of the hazards. And then we'll just distribute the energy among the customers by developing another network called distribution systems. Every time you switch a light, the electrons basically flow all the way from the generation units through the transmission lines and through the distribution. And you are basically relying on a tremendous network of energy infrastructure that literally kind of stretches across the country. So power plants, pipelines, transmission wires, storage facilities are all just part of this huge system. And maintaining the reliability and security of this system and also providing the power with a reasonable price is actually the objective of all the operators that are basically maintaining this network, so then the customer can actually use the power with a certain quality that expects. It basically means that you're not expecting to plug in any of your devices and then get like a random voltage there. So maintaining the voltage, the frequency of, let's say, 60 hertz in US, this is a crucial task that is basically done by a lot of engineers and operators in the system. Now, much of the US energy systems predates in the early 20th century. Most of the electric transmission and distribution lines were constructed in the 50s and 60s. And by then, they would actually have a 50 years kind of life expectancies. The system is not really designed to carry the load that it is carrying now. It was not designed actually to serve the severe weather conditions that we are facing these days. From the 1950s to 80s, the significant power outages average around a few per year, like around few, close to 5 per year. In 2007, they were increased to like 76. In 2011, there were over 300. So we'll start to see more and more such events, so such dramatic power outages. As you see in the figure on the top left, you can see it here. This figure shows the top biggest blackouts in the US history. As you see here, Hurricane Maria that hit Puerto Rico and US Virgin Islands in 2017 had the longest power outage based on million customer hours in the US history. This prolonged outage basically caused a lot of problems. They caused health and environmental crisis because the power was cut to a lot of water sanitation facilities, and also medical facilities, medical devices were actually out of power. And it causes a huge amount of a loss during the pretty much long period. The other thing that you can see in this graph is that as you skim through this, you'll see that the top 10 outages here, out of these top 10 outages that you can see here, 9 of them actually happened after 2000. So that basically means we're going to see more frequent kind of incidents like this, more frequent severe weather conditions. The figure on the right side, this figure, is basically showing extreme events that causes economic loss of over $1 billion. So you can see that basically 2020 is actually keeping the breaking record of the number of incidents that actually causes such loss. So in 2020, we had around 22 actually of such events that caused over $1 billion loss. So these outages, as you can see here, this extreme weather conditions that causes outages, they are very costly. I'm giving you some figures to get an idea of how costly they are. So the kind of estimated outage cost for a medium to large industry for like 30 minutes is approximately around $60,000. If it goes to 8 hours, the cost will be $94,000. So between 2003 and 2012, these weather-related conditions, these weather-related outages that are basically coupled with this aging infrastructure, a lot of them were not basically renewed or expanded more. There were these events caused economic loss, an estimated economic loss between $18 to $33 billion. And not to mention that one of the things that are very important here is that some of these losses that you basically cannot really put any price tag on it. And that's by the time that you're dealing with people's lives. And at that point, losing precious lives of many people in these incidents, it is going to be much more, it has a catastrophic kind of impact rather than just boiling down everything to numbers. So these are basically causing these incidents along with this weak infrastructure system that we currently have. It's basically an aged power, I should say, infrastructure system causes a lot of issues. And that's why that you can see the American Society of Civil Engineers just gave the entire energy infrastructure a barely kind of passing grade of D+. Okay. In the figure on the right-hand side here, you can see that in 2020, these are the events that happened in 2020. You can see you have this 22 weather climate disasters that we just saw in the figure above. And you can see the kind of the types, as you can see here, a lot of events like kind of hurricanes, snowstorm, wildfire, and all that. So it is kind of differentiated based on the type of incidents. And what is important here is that once we're defining resilience, we need to basically be careful about resilience against what kind of incidents, because the kind of measures that we have and the kind of actions that we take will be very much dependent on the nature of the extreme weather condition. So in order to define resilience, I came across a report by Pacific Northwest National Laboratory. This was a very interesting report. I took this kind of figure from that report that basically, this report, one of the objectives of that report was basically to try to define the meaning of resilience and differentiate it with what we call reliability. Of course, there are many kind of definitions of resilience. give you an example, like EPRI, the Electric Power Research Institute, defined resilience as prevention, recovery, and survivability. The other definition by National Infrastructure Advisory Council on the resilience is the ability to reduce the magnitude and or duration of disruptive events. National academies defined resilience as the ability to prepare and plan for or absorb, recover from, or more successfully adapt to actual or potential adverse events. The Presidential Policy Directive resilience is defined resilience as the ability to prepare for and adapt to changing conditions and withstand and recover rapidly from disruptions. So resilience basically includes the ability to withstand and recover from deliberate attacks, accidents, or natural occurring threats or incidents. But this report specifically presented the grid resilience as the ability to withstand grid stress events without suffering operational compromise, or to adapt to strain so as to minimize compromise via graceful degradation. So once an event happens, and that event could be any type of event, could be an accident, could be due to kind of catastrophic events that you get like many contingencies, we will basically take two approaches. One is designing the grid so then we can resist the stress in a passive way, or we could do some certain adjustments to basically deal with this unfavorable scenario. And basically by doing this, we're trying to maintain the energy kind of supply continuity to the customer. So the customer would not see any disruptions at that point. However, when we are getting to the point that we couldn't keep the customers and the system suffers from outages, that is the domain that reliability indices would kick in. So reliability is different from resilience in the sense that resilience means you don't want the customer see any disruption at the end of the circuit, rather than reliability, or basically means that you want to recover and reduce the suffering of the customers in terms of frequency of the durations and the frequency of the outages and duration of the outages, so the customer would not suffer much. But eventually reliability begins by the time that the resilience ended. So the point that resilience could not be served or supplied here, then we'll see more reliability indices to be measured. And another important thing is reliability measures. We have like certain measures of the power system. We have the measures we call CAIFI, for example. CAIFI is Customer Average Interruption Frequency Index, or System Average Interruption Frequency Index. That's basically the average number of the average number of incidents that happens, the average number of outages that happens in a system. We also have duration indices like KD, like Customer Average Interruption Duration Index, and System Average Interruption Duration Index. These indices are specifically used for reliability, but some of these indices, especially for the frequency of such outages, would give you an idea of resilience as well, because the minute that you have these frequencies and reliability, you basically could not actually satisfy the resilience of the system. So it is kind of related in that sense, but these indices are basically designed for reliability measures, not specifically for resilience. And coming up with an index for resilience is really tough. Resilience, according to this report, actually, resilience is a kind of a system characteristics. It should not depend on the operation practices. It should be a kind of a, and also the other operators' behavior. It should not depend on those. It should be a system characteristics. And that's why that is really tough to define an index for resilience in that sense. For the reliability, you would see that we are dealing with two different kind of issues. One is the adequacy, which basically means the ability of the system to supply the aggregated demand. So you have enough generation capacity to serve the demand and other energy requirements of the system. Or you can actually operate under contingencies, which basically means that the system has the ability, the bulk power system has the ability to withstand sudden disturbances, such as short circuits or partly like anticipated loss of part of the system, But these are basically contingencies, either single or double, that the system can withstand with, with certain, would not violate certain, let's say, frequency or duration indices. So duration, outage duration or outage frequency indices for the customers. For example, we'll say that the customer, we don't want a customer suffer outages more than, let's say, 100 minutes per year. So anything that happens in the system, we don't want the customer to see outage over 100 minutes per year. And that's how we design a system. So if there is any single outage somewhere in the system, or we have other types of losses, the customer, the power supply to the customer will not be cut. So this is basically the reliability that we are talking about. However, when we are talking about resilience in a power system, the system is so large that basically reinforcement of the system to the level that you're not going to see any outage at any time for any event is pretty much impossible. So that's why that for the resilience of the power system, we also kind of focus on recovery and restoration of the customers as soon as possible. It's not just reinforcing the system to the level that nothing happens, but also if something happens, we want to recover as soon as possible. And basically we divide the resilience, once we want to ensure the resilience, we're dividing the time scope into two different periods. One is the pre-event preparation, the other one is the post-event recovery and restoration. In the pre-event preparation, we can take many actions. One of them is basically expansion of the grid, and this can actually happen both on the transmission level, as you can see here, in the large scale transmission level, and also in a low voltage distribution level. So expanding the resources and also allocate certain resources, and those resources are not just generation. It could be transmission lines, it could be distribution lines, it could be also crews and repair and the pieces of equipment that we need for repair and restoration. So expanding these, allocating these resources before an incident happens is very important to improve resilience of the power system. The second action that we can take is reinforcement. Reinforcement of the infrastructure system could be in terms of construction, for example. An example of such construction is that instead of having overhead transmission lines, let's bury power lines under the ground. But again, as I said, it is very much dependent on the type of incidents that we want to basically deal with. If we are talking about wind gusts, this is a good idea. But if we are talking about earthquakes or floods, burying it on the ground would cause more trouble, actually. Okay, so it is very much dependent on the incidents that we want to deal with. Or we can also design a kind of stronger conductors or robust towers that can actually stand natural hazards more efficiently. But at the end of the day, as I said, we cannot really prevent the disruptions with even all kind of things that we could do at that point. The other action that we will take usually on a kind of daily basis in a power system is the inspection and maintenance. So there are a lot of technologies that are being used, including drones, that are just inspecting any fractures or issues with the transmission lines or distribution lines, looking at the health of the power system, and also like the maintenance of the generation assets that you have, especially for the thermal power plants that they have like these large turbines and engines. Then we need to basically maintain them to make sure that we will have sufficient power by the time that we need even more power in extreme weather conditions. I'm going to talk about it a little bit later, but that's a very important thing. Another important thing that you can see in this figure, which we basically do it again in a normal condition, and also we're going to use it as a pre-event preparation for our system, is situational awareness. Situational awareness is very important for the power grid, given the size of the power system, which are basically, we have lines that are 1,000 miles, and the system is very large. Then situational awareness, knowing where we're standing, what is the operating point that we are working on, is very important in the power system. It is important both on the transmission level and also the distribution level. So that's why that in the transmission level, we have measurement devices, as you can see here. These could be phasor measurement units, we call them PMUs, or it could be RTUs, remote terminal units. These are also relays, all kind of measurements that we can take from the system, getting the voltages, currents, connections, topologies, all those things should be kind of collected. The health could be also measured by having different types of sensors. It could be sensors that measures the current, the temperature, the tension. It could be also providing visibility by dispatching drones, looking at the infrastructure system, make sure that everything is fine, or if there is any outages or there's any fatigue in any line, we know it ahead of time so we can actually plan for doing maintenance on it. And in the distribution system, which is kind of these kind of practices are getting more and more momentum. We also look at having smart meters. We call this AMI, advanced meter infrastructure, or smart meters, developing smart meters. So then we can actually have real-time information from the customers and know that if they're connected or not. This is very important. This is a kind of new things that happened actually by once the kind of notion of smart grid actually came on. So, and for processing this data, as you can see, for transmission level and distribution level, we are collecting a huge amount of data. So we are now relying on more artificial intelligence techniques to give useful information to the operator. The operator cannot really collect all these data and process them in a real-time basis. So developing algorithms for artificial intelligence algorithms to actually deal with this huge amount of data is very important. And also utilities in distribution systems are heavily relying on these customer meters installed in the customer. These are smart meters. Before, the practice was if there was anything wrong with the distribution system, the operators, the utility companies are still received calls from the customers. So they didn't know what's going on, and then they were notified by the customers like that. But right now, with those new technologies that are available, the utility companies would be aware of such outages based on the data that are received by these meters. And these data are basically updated by, it's around 15 minutes. Like you got a signal every 15 minutes. So it is a kind of counted as a very fast kind of detection of the loss of customers. Another thing that is very important, as I said, is state estimation of the power, both in the distribution system and also in the transmission level. And also new technologies that have been developed, like smart switches, smart relays, that you can actually change the topology of the network by clicking a couple of buttons rather than sending somebody over and start turning on and off the switches. Okay, so this is also very new. It actually relies on an effective communication infrastructure system that can actually send the signal from the operator's room to the switches, and also collect back the data that we are getting from all these smart devices. Now, with these kind of technologies, we saw huge improvements in recovery. I'll give you an example. In Hurricane Harvey, when it was hit Texas in 2017, some utilities took them weeks to basically restore the electricity to the customers. However, there were other utility companies that they basically could recover 95% of their customers in 24 hours. And that is basically with a very efficient outage management system and basically leveraging all kind of these new technologies that they could basically estimate the state of the system really quick, know where the damages are, try to isolate those damages, and then they try to restore the system as soon as possible. And I'm going to discuss that on the next section where I'm talking about the post-event kind of actions that we can take. So this is basically what we do if you want to prepare for an extreme event condition. In the post-event recovery and restoration, given the preparedness that we had before, we start to basically manage the system. And the way that we do it, we actually first will detect the faults. So we have a kind of a scheme called it fault location, isolation, or service restoration. It is a kind of automatic system or automatic service. So if there's any fault or failure in the system, first we automatically detect the fault. We know where the location is. We try to isolate the fault so then the power is not going to go through the faulted area. And then we're going to send crew and equipment to restore the damaged part of the system. Okay, and this is very important. Restoration actually at that level is very important because a lot of infrastructure systems are also dependent on power. When Hurricane Harvey hit Texas, I remember that there was a shortage in fuel in Dallas, and the reason for that was a lot of refineries were actually shut down at the time, and that caused basically shortage of supply in the fuel system. There were also, you can actually also even guess what would happen to the healthcare system, transportation system. So a lot of these systems, water supply system, a lot of them are actually dependent on electricity. And the faster that we can recover, the faster the other infrastructure systems would actually recover, because most of them are being served by the power. And this kind of responding to these kind of events is not just a matter of putting technology into the system. It also needs effective coordination among federal, state, regional, and local, utilities and entities. So the grid modernization that we currently have and smart grid technologies that is it's been around for some time now may not be just the only thing that needed for improving the resilience of the power system. We also need coordination among people, among processes, among these new technologies. I'll give you an example, coordination between transportation network and electricity network, because these crews were basically being dispatched through roads. So if you have incidents on the roads, if there are trees falling on the roads, and you have some roads are basically closed, then this coordination between them to dispatch the crews in a way that they can reach certain locations as fast as possible would be an important thing. So it's not just focusing on power, it's basically focusing on coordination between these systems as well. And as I said, if we have this real-time damage assessment by collecting this data from the power system, if we can assess the damage as fast as possible, have a very good visualization of what's going on in the system, and then manage our assets, the crew, the equipment, and we could dispatch them effectively, we can restore the power very quickly, okay? So these are the things that we do in a pre-event and post-event recovery. Now, what are the technologies that are being used is basically microgrids. Microgrids provide resilience because the definition of the microgrid is that we have a system that can be isolated with its own resources. It has a certain boundary. We can basically allocate generation to the load and use this system to serve the load. So we're not depending on any other power system. And we have some kind of examples before that this system was effective. One of them was in Superstorm Sandy in 2012, where basically New York University campus used the microgrid that were powered by gas turbines and steam turbines to serve the campus. So these are kind of examples that this system worked before, and we are looking more and more into this kind of technology. And this technology can actually have different boundaries. You can have small microgrids like consumer microgrids, just a generation or a storage close to a load. One important thing is that all of them can be isolated from the network using this switch. So this is called point of common coupling. You can disconnect it and then use this battery to serve the building. And it could be also larger, which like feeder microgrids, partial feeder and also feeder microgrids. And it could be even bigger, like substation microgrids. So depending on the size, you can have different types. Now, what are the objectives of having these microgrids? Aside from resiliency, that you have like your generation close to the load, we can also have a better operation. Economically, it's better. Why? Because if this microgrid is actually kind of connected to the grid and the price of grid goes up, you can actually cut this and use your own resources. And if anything happens in the microgrid, for example, a fault happens here, there's a short circuit here, you can isolate this by opening these switches, and then this customer that is out of power now can be served by switching a redundant line here and serving this customer. This is called fault location, isolation, and recovery through automation. And of course, if you have crew, you can send them over and repair this line later. Okay? That's how we actually operate microgrids, and that's how it contributes to improving resiliency. This is called also self-healing, as you can see here. This is one of the functionalities of the microgrid. It could heal itself by doing certain actions, so the customer will not suffer from long outages. There are other functionalities that I'm not going to discuss, but other functionalities that the microgrid can provide, aside from economics, is basically connecting back to the grid. These are the kind of functions that the controller of this microgrid should be able to do. And also emergency demand response. What is emergency demand response? Is that sometimes the utility companies are short in supply, and they call customers, let's say SMU campus or other customers, to say that, can you cut the power by 25%, 50%, because we're short in power. Now, if SMU or other campus here has its own resources, they can actually supply the load without really reducing the load by local generation assets, and basically provide that kind of service to the utility company that basically was short in power. So this is called emergency demand response. The demand can respond in emergency conditions. So these are all the functionalities of the microgrid. Now, once we got a lot of these microgrids, we can actually build a system we call network microgrids. You have a power system that energy can be exchanged with certain price, and now these people, these entities can actually work together. So depending on the price of the electricity there, we can have exchange electricity between microgrids. They can sell and also buy back energy from the distribution network. And this is by the time that we're having this concept of transactive energy architecture, where not only we have it in the larger scale, which is transmission level, big generators, but also in small scale levels in the distribution system. If you have a generation source and you want to sell the electricity, you would be able to do so if you have this small market in the distribution level, in a low voltage level. So this is the idea. Now, I'm gonna just talk a little bit about multiple energy carrier microgrids. Those are microgrids that are supplied by different energy carriers, like natural gas, for example. And they will basically serve customers with different needs. Customers may not just need electricity, they may also need heat. Now, that heat could be provided by a different type of technologies. It could be like a burner. You can have a gas burner, just burn gas, as you can see here, and produce heat. But you may also have a combined heat and power unit, where basically we generate electricity, but also not only we generate electricity, but also we generate heat. Okay, so this is a byproduct of electricity, because once the engine is working, it gets hot, you can use that heat to serve the customer's need. So then we're looking at interdependency between energy infrastructure systems. Natural gas and electricity work together here. Natural gas can produce electricity in a small scale. And this coordination would be actually increases the complexity of our system. So this is another type of system that we can work on. And in that perspective, I just want to talk about the resilience of this kind of system, that we can actually highlight the interdependency between different infrastructure systems, different energy infrastructure system. Here is basically natural gas and power. If you think broadly, we also have water infrastructure system, because a lot of these water pumps actually work with electricity. So the minute that we cut electricity, water treatment facilities are gone, water pumps are gone, and also gas pumps are gone. They are interconnected. Electricity serves gas, gas serves electricity. So these are all interdependent systems. So in this one, this is basically a title of one of my research that I did before. I just looked at the resilience of these interconnected infrastructure systems from the perspective of attack and defend. So I assume that we have an attacker some point here that wants to basically cut as much as energy lines as possible. It could be pipelines, it could be power lines, it could be generators. And I have a system operator which wants to minimize the impact of such kind of attacks or such kind of disruptions. Okay, so it's like a classic game between an attacker and a defender in a system. And what we get through this kind of simulation, we get what are the vulnerable parts of our system? What are the vulnerable components of our system? As an example, let's say we have this kind of microgrid. This is a microgrid. These are energy hubs. These are the facilities that convert natural gas. These are natural gas pipelines. These green ones are electricity lines. So these are converting natural gas that's served here to electricity and send it to certain loads. Okay, let's say this is a very high priority load, and as an attacker, the attacker wants to attack the system, try as much as disruption as possible. But the main objective of the attacker is to hit basically the most important critical load, which is basically the high priority load here. Okay, so if we simulate this through an optimization, and I'm going to show it later how it works So this is basically the cost that I assumed for any disruptions, and also the cost that I'm going to reinforce the system. But I'm going to skip this. I'm just going to show the outcomes. So if the attacker wants to cut this load, it targets outages like this. It tries to cut the electricity loads and also a pipeline. So then this generator would not work. It cannot serve this load. So it creates islands here. It creates as much as damage as possible. And these damage can be actually kind of turned into dollar amount. As I said, if you're losing the process in some facility, it turns into economic loss. So this is what happens in the first attack. Once you know, okay, I have these vulnerable lines here, I'm going to reinforce these lines, make it stronger. So then in the second attack, it's either cyberly would be reinforced, or it could be physically would be reinforced. But then the next round, the attacker needs to spend more budget, more effort to actually cause disruptions here. Okay. So if you do that in the second round, the attacker goes with these lines, try to disrupt these lines, still attacks this line. See here? So again, I'm going to see this and I'm going to reinforce my system at the second level to basically make sure that in the third round, the attacker will not go for those lines. And I'm hoping for that. So on the third line, you see, again, cutting this load is so important to the attacker that's going to spend more money even here, okay, to cut this line. So that's also another incident that could be covered. Now, if we go on and on, you see that the scale of this is going to get large. So you're going to get a more connected kind of system. And eventually, you can see that the cost would reduce after you're reinforcing the system, but then you spend more money on reinforcement of the system, these two, okay? So then, as you can see here, then the total, the sweet spot would be somewhere here, that the cost of losing the system and also reinforcing the system would be minimized. Okay? The other research that I did, I'm going to go through it really quick, is the economics, the way that these guys are actually interacting with each other, sell energy and buy energy from the system. This is the wholesale market. This is the distribution market, and you can see exchanging of dollars and energy here. And we'll see different strategies again on the suppliers. As an example here, you can see here. So you have this distribution network. You have somebody that basically interacts with a large-scale power system. And depending on the scenarios that we can deal with, you may, let me skip here and show it here. You may buy energy, basically buy energy from the power system to the distribution system, or you may sell energy back to the power system, depending on who provides cheaper power. So this is another research that I did, basically capturing the interaction between microgrids and a large-scale power system that you have, like large-scale generators in a system. So I'm gonna end my presentation by just summarizing some of the concepts that we covered here. So we saw that improving the resilience of our power system is very crucial. We saw the difference between resilience and reliability, and then this multi-stage decision-making process that we need to maintain resilience, the pre-event and post-event decisions, and also the interdependence between energy infrastructure systems is important. And also we look at the concept of transactive energy. Once you get these small microgrids, how they interact with each other to provide a cheaper power and facilitate this energy transactions in the grid, in the distribution grid. With that, I'm going to end my presentation. If you have any questions, I'll be happy to address.